Okay, this is chapter 5 on drag. Um, a lot of these equations are going to be similar to what we did in chapter 4 with lift. So let's go ahead and begin. Drag is going to be equal to the coefficient of drag times dynamic pressure times surface area, which is equal to coefficient of drag times the density ratio times airspeed squared times surface area divided by 295. And if we want to solve for the coefficient of drag, it's going to be equal to drag divided by surface area divided by dynamic pressure, which is equal to 295 times drag divided by density ratio airspeed squared times surface area. So there are your equations for drag. Similar to the CL alpha curve, you'll see sometimes this is plotted with CL and coefficient of drag. So you'll have CL alpha and CD alpha graphs. So if this is angle of attack, CL, CD, normally what you'll see is a CL looks something like this, and then a coefficient of drag that looks something like this as well. Okay, so as you're approaching CL max, you're approaching your highest level of coefficient of drag as well. The next thing that's important is the lift to drag ratio. So, and this is important especially when you talk about engine out and best glide, and that's where this comes from. So lift over drag is going to be equal to coefficient of lift divided by the coefficient of drag. And similarly, you'll see plotted, this is angle of attack, CL, CD, CL looks something like this, CD looks something like this, and your lift the drag looks something like this, where this is L of D max at this top point. Okay, and then on the right side you would be able to read your L lift the drag component. So the highest point in this curve is important because this is L over D max, and L over D max is going to be your most efficient angle of attack and where minimum drag occurs. And if we're under 1G flight, which most of us are in general aviation and commercial aviation, lift to drag is going to be equal to weight divided by drag. So another important to understand is airspeed for lift to drag max varies with weight. How do we know this? Equation 4.2. So if we go back to 4.2, is anybody wondering what 4.2 is? CL. So lift is a component that's going to vary with weight. The next thing you'll see is something called induced drag, which is normally DI, and this is the least understood type of drag, but it's also the most important. Induced drag is important at low air speeds. And it's normally the drag due to lift. So as we're producing lift, we're also producing some induced drag. If you look at figure 5.4, it shows the various components of a wing, specifically aspect ratio, the wing area, the wing span, and the average chord of a airfoil. I'm sorry, not airfoil, but of a wing. I'm going to draw one here for you. This is tip, root, we normally call this gamma dihedral, B/2, and we'll call this C bar, meaning average chord. So similar to what you see on page 5.4, I just simplified it a little bit in my version here. So just make sure you understand, spans the entire length of the wing. So if I drew another wing, this is going to be B. You know, this is going to be short, but if I had the other side of the wing and that second figure on page 64, this entire piece would be B, so I just drew one half of the wing, so that's why I say B/2. C bar, the root of the wing, the tip of the wing, and the dihedral of the wing. Okay, look at page 65. There's some information there on the definitions of wing. And then let's look at wingtip vortices. So at the we're going to have wingtip vortices here, normally somewhere in the middle, and at the end occurring. Your biggest wingtip vortices, normally the highest point, is going to be at the end of the wings. Now, this is why you'll see spoilers on airplanes to reduce these wingtip vortices and use the wingtip vortices to the airplane's advantage to push more lift over the best area or aerodynamic force to get you the highest lift component. And if we get this, we will get better gas mileage, so we'll increase fuel efficiency, and that's why you see a lot of the spoilers on commercial airliners. Another important part of this, and this is really important in not so much commercial aviation but in military aviation, is role reversal, especially in high fast airplanes, flying in formation. The wingtip vortices are occurring here, and you can get something called role reversal that can hurt the handling qualities of an airplane. So just a little bit of a sidebar if you're going to go fly military and formation flying. A lot more things to be aware of. Okay, on page 66 and 67, you're seeing more depictions of how relative when drag occurs. I'm not going to go into great detail here. This would take us a long amount of time, so I expect you to read some of that. I'm pointing out the high important things that's occurring here. On page 68 in figure 510, you'll see relative wind and force vectors that act on a finite wing due to drag. So we're showing the effective lift, total lift due to induced drag. So there's total lift, but as we said, lift is going to induce some drag. So when we refer to effective lift, it's lift. This is probably not mathematically correct, but for explanation points to make the point, effective lift is equal to total lift minus induced drag. It kind of gives you the concept of what effective and total lift is. And like we said before, the most critical condition where induced drag is greatest is during low speed, high CL flight with a short wingspan aircraft. So, your most critical condition is low speed, high CL, low aspect ratio aircraft. Critical phase of flight. If you look at page 69, they're going to give you a summary of induced drag. On page 70, we talk about ground effect. So low wing aircraft are going to be more affected by ground effect than high wing aircraft. This is where we get the float during landings. So to reduce this floating tendency, the aircraft approach is normally made with some throttle on instead of at idle. So once we get into ground effect, we have a little bit of throttle, then we close the throttle and the aircraft is flared. And this reduction of drag is compensated by reduction in thrust, and then we reduce the floating action. Important here on page 71, it says, a word of caution to pilots of turbine engine aircraft. Fuel consumption is high for aircraft at low altitude, so the benefits of ground effect may be nullified by poor fuel consumption. So ground effect can influence many aircraft. During takeoff, as the aircraft leaves ground effect, the opposite pitching moment occurs. Here the increased downwash hits the horizontal tail and causes a download on it, and a nose-up pitching moment results. Unless corrective action is taken, this will cause a sharp increase in drag that, when coupled with the increase in induced drag that results when an aircraft leaves ground effect, may prevent a successful takeoff. So this is another important thing in aerodynamics. The third effect of a flying in ground effect occurs to the aircraft that have static airspeed ports located below the wings. This creates a false reading from the airspeed indicator. It will read lower than the actual airspeed on entering ground effect. If this goes unnoticed during takeoffs and landings, but in long flights over water when trying to take advantage of ground effect, it may upset a pilot to see the airspeed decrease as the aircraft approaches the water. So we're not going to get into much of that because that's dealing with more water landings, and I don't think we need to go there for this specific course. So on page 72, you want to summarize ground effect. On entering ground effect, induced drag is decreased, nose down pitching moment occurs, and the airspeed indicator reads low. On leaving ground effect, induced drag is increased, nose up pitching moment occurs, and the airspeed indicator will read higher correctly. Also on page 72, there are other types of drag that occur. Parasite drag, skin friction drag, form drag, interference drag, leakage drag, and profile drag. And then they give you the equations for the various types of drag that occur. You can read that. And then what I want to get to is total drag. So total drag is going to equal to induced plus parasite drag. And then if you look at figure 5.5, it shows the total drag curve. I'm not going to draw this one because you can see this is getting more complicated as we start to add more and more components to these graphs. And also with the equation in 5.7, I'm not going to write this out, but this is a more thorough equation for total drag. And I believe that's it. So take a moment and read through. I think we went through most of this up to page around 69. So read 69, 71, 72, 73 to make sure you have an understanding of the various types of drag that occur. And if you have any questions, let me know. And this concludes Chapter 5. Thank you for listening.